Bismillahirrahmanirrahim. Welcome back and good afternoon, ladies and gentlemen. We are honored and delighted to be joined by our keynote speaker, Associate Professor Dr. James Wilton Ely, and our panelists, Dr. Thomas Weinberger, Associate Professor Dr. Amir Shaharuddin, and Associate Professor Dr. Amjad M. Hussain. Welcome, gentlemen, to i-ConSPADU 2021.
Thank you very much. It's great to be here.
Ladies and gentlemen, we shall now proceed with our keynote speaker, Associate Professor Dr. James Wilton Ely of Imperial College London. Dr. Wilton Ely was leading research groups at the University of Oxford and University College of London, and currently holds the position of Reader, Associate Professor in Inorganic Chemistry in the Faculty of Natural Sciences, Department of Chemistry of Imperial College London. He has extensive experiences in coordination and organometallic chemistry of metals from group 8 until 11, and their uses in catalysis. He is also the recipient of Sir Geoffrey Wilson Award of the Royal Society of Chemistry. Apart from that, he is one of the directors of Masters by Research Green Chemistry Program, founder and former co-directors to Masters by Research in Catalysis and the Advanced Molecular Synthesis. Currently, he is the Director of Postgraduate Studies and a Fellow of the Royal Society of Chemistry. With no further ado, ladies and gentlemen, please welcome Dr. Wilton Ely.
Thank you very much indeed. It's very kind. And I'd like to thank you and also the organizers for the invitation to speak today. And I think it's a fascinating conference. I've had a look at the information online, and I look forward to answering some of the questions if you have some after my talk. I'll start by sharing my screen, which should hopefully work. Right, if someone could just let me know that I am sharing on full screen mode. Is that working okay?
Everything is good.
To check. Yep, good. Okay, thank you very much. Right. Well, thank you again for the invitation. It's great to be here and talking to you today. I'd like to talk to you about various topics that we're exploring in our research laboratories at the moment. The topic that I'd like to focus on first, though, is biorenewables and how we can use those to create the platform chemicals we need to be able to create our material world, because at some point we are going to have to rely on something other than oil to be able to make the chemicals from which we make our pharmaceuticals, from which we make our polymers. And of course, this is incredibly important since we rely so much on both of those things in our modern world. The second topic, which is shown below here, is focusing on another very, very, very important aspect of sustainability, which is recovery and reuse of metals and elements in general, which we're using at an alarming rate, and many of these are very, very scarce. And I'll talk a little bit about our work, which we've been using, mild approaches to be able to recover palladium from used catalytic converters from cars to make new catalysts. Okay, so this is the structure of the presentation. I won't spend too much time on this slide, but just to give you an overview of what we'll be talking about and a couple of summary slides at the end. So Imperial College, for any of you who don't know, the institution is in London, and there's a picture here of the university in its original campus in South Kensington, which is very nice. Leafy part of London. You can see that it's right next to Hyde Park. It's a major research university in the UK, just dedicated to science, technology, medicine, and engineering. And it has a very, very international outlook. It has almost 50% of the students coming from outside of the UK. We have a very, very nice, very vibrant atmosphere, and there are many, many Malaysian students at the university, and we very much enjoy having them there. And I'll just mention at least one student who's involved in the research that I'm going to present today from Malaysia. There have been a number of very eminent researchers who have come out of Imperial College over the years, and these are some of the ones that some names you might have heard of, perhaps Alexander Fleming, who the discoverer of penicillin and its effects, but also there are various chemists as well. So Sir Geoffrey Wilkinson, who is shown here, was mentioned in the introduction, and I actually overlapped with him very, very briefly at the beginning of my time as a student at the university. I think the message really from this slide is that there's been a long tradition of science, technology, and engineering at the university, and this is something that still continues very, very strongly today. We have recently moved 2 or 3 years ago now to a new campus, which is a number of miles away from South Kensington campus, and these have allowed us to create state-of-the-art new laboratories. It's called the Molecular Sciences Research Hub. This is where the work that I'm going to talk about today was carried out in part, and it's a very, very nice state-of-the-art facility, and perhaps if anyone is visiting, please do get in touch. I'll be very happy to show you around. So, biomass, why is it important? Well, I'm sure that many people on the call today are very aware of biomass as an important feedstock, but I'd like to talk a little bit about how we can use biomass in particular to create platform chemicals. So these are the chemicals that we rely upon to make our polymers and lots of other chemicals that we really have built our modern world around. So it's well established that we are consuming oil far faster than it can be replaced by nature. And this is obviously a great concern. And at some point, we're going to have to think of alternatives, and that time is not very far away. We have a number of different alternatives that we could use as alternative fuels. We have wind, offshore wind in particular in the UK is very, very established now, and it's hoped that a very large proportion of the UK's energy needs can be met by wind. But of course, that depends on the situation. We have a fairly windy island, which helps to some extent to be able to supply that energy. Then, of course, solar. I think that's something that Malaysia probably has a lot more of than we do in the UK. But that's obviously going to be a very, very important aspect to be able to supply our energy needs. Nuclear, somewhat controversial, of course, but it's still a major mix for many countries, in particular France and Japan. But as the Fukushima disaster showed, I think nuclear is it certainly has its risks, and it's something that I think people are using as a bridging energy technology at the moment. I don't think people are planning to rely on nuclear solely. Hydroelectric power, of course, very, very important, but it does require the right geography to be able to do that, and many of the rivers that are suitable for this have already been dammed and are being used already, so it's not something that can be expanded indefinitely. And then lastly, we have biomass. There are other forms of energy as well, which I won't go into, but these are the ones I'm just focusing on today. And biomass, the last on that list, and the one that is going to be the focus of my talk today. So one of the nice things about biomass is it's very widely and reasonably evenly distributed. I mean, it depends on how much land mass you have, but it's something that isn't only found in certain parts of the world, such as oil. That's an important point. Many, many countries have sufficient area and the ability to be able to grow crops, which then can be used for biomass. It's generally considered carbon neutral. Of course, one has to be careful, and that's why I put it in inverted commas. It is carbon neutral in the sense that the carbon dioxide from the atmosphere is incorporated into plants, and then that carbon becomes available for use in biofuels and platform chemicals, but at a cost of processing, of course. So there is extra energy that needs to be added through the processing, so it's not completely carbon neutral. However, we are at least not adding new CO2 to the atmosphere when we burn, for example, biofuels. It is using CO2 originally that was in the atmosphere, perhaps months before. So one of the big issues is how do we do this responsibly without competing with food production? This is a big issue that's revealed itself in the very beginning of biomass and biofuels in particular, because we often use good land to grow the crops which we use for for biomass and hence biofuels. And that's a big problem because that competes with food crops. And I think it's very clear that we are now moving very much to using non-arable land, the land that's not suitable for farming, to be able to make our biomass that we use for making biofuels or platform chemicals. And this can include lots of different sources, so grasses, scrubland stover, which is the waste that's left over after cultivation, after gathering in the crops, and also generally agricultural and food waste. And these can all be used to make platform chemicals and biofuels. Another key factor I think people often forget is that the availability of petrochemicals. So when I, as a chemist, buy something for use in our research, it's very easy. You just go online and there are big chemical companies that supply all these things. But these chemicals rely on the fact that we extract oil for fuel, because that is what drives the economics of chemicals. So if we stop, for whatever reason, whether it's our own choice to stop or whether we start to run low on oil, and both of those are very real possibilities, then we will have a big problem, because the lighter fractions, the petrochemicals that come out of the drilling process, will no longer be available, certainly not at the same price that we're used to at the moment. So if this stops, where do we get our chemical building blocks from? And this is really the subject of the first part of my presentation today. And I would suggest that biomass is the only alternative to be able to create these building blocks. So this is a scheme of the carbon cycle. It's got the carbon energy cycle, I would say. So we have the sun shining on the trees and carbon dioxide being incorporated into the trees, and then this is harvested, processed, and then separated out into the different parts of lignocellulosic biomass, so cellulose in particular, which then can be broken down using enzymes in a biorefinery to create sugars, which then can be used in various different ways, and microbes are mentioned here, but I'll show that in the research that we're doing today that biological processes aren't necessarily needed to create the platform chemicals I'm talking about. And here the focus, as shown here, is on biofuels, and we can then put these fuels into our various different vehicles, which then, once those fuels are burnt, produce the carbon dioxide that goes back into the cycle, and the whole thing can start again. And in particular, I should point out that for plane travel, it's difficult to see beyond biofuels, really, because we are so reliant on a liquid fuel that it has a high energy density, which is very difficult to be able to supply using solar, for example. So a little bit about biomass and plants in general. So we have crops of various sorts, and this image suggests a plant that perhaps is grown on scrubland rather than good arable land. But nonetheless, all of these are essentially very, very similar. You have the cells of the plant, and in the cell, beyond the cell wall, you have the lignin, hemicellulose, and cellulose components. And these can then, if they can be separated out, we can make use of the lignin, which is perhaps the most difficult to use part of the plant, though there is quite a lot of work on developing carbon fibers, for example, from lignin. But the hemicellulose, and in particular the cellulose, can be used in lots of different processes. So cellulose is what we're going to concentrate on today. This can be thought of being made up of essentially glucose type units, all lined up in a long chain. And so cellulose is very abundant. It's around between 50 and 70% of all plants, and it's the most abundant naturally occurring organic polymer on the planet. So what are ionic liquids? It's something that I'm going to be mentioning a lot today, and so therefore I think it's very important to give you an overview of what ionic liquids actually are. So you'll be familiar with a salt such as sodium chloride that you might put on your food, for example. If you heat that at around 800 degrees centigrade, it starts to melt and you get what's called a melt, which is the ions, the sodium ions, the chloride ions dissociate and then are free to move around in a liquid. Now, an ionic liquid is also a salt, like sodium chloride, except that it exists as a liquid at very low temperatures. Usually classified as being an ionic liquid if it's liquid in liquid state below 100 degrees centigrade. And so they're composed of ions, cations and anions, but they're ones that are rather different to sodium chloride, for example. They're designed so they don't crystallize. So unlike sodium chloride, they don't easily form crystals, and so that makes them much easier to isolate in a liquid state. And so some examples are shown below here. We have some cations here, and you can see they're quite bulky cations. You see that they have chains which are unsymmetrical on either side. And then we can have anions, such as these ones down below here, which don't pack nicely with the cations, and hence when you bring a cation and anion together, they form a solution at room temperature rather than solid. So we have many different possible combinations. There are literally millions of different combinations that you can think of, given all of the cations and anions that are available, and also the tunable nature of these species is very, very important. So you can change the properties in terms of the hydrophobicity or hydrophilicity of these liquids, just by changing the structure, the chemical structure of the cation and the anion. And this is very, very important. We can then make them able to dissolve different types of compound, or render various types of compound insoluble if we wish, to be able to help with our processing. So the interest in ionic liquids has grown massively. The early days, just at the beginning of the new millennium, we only had a relatively small number of papers that were published each year, but this has now increased to a great extent. So we have a huge amount of activity using ionic liquids in various different applications, but particularly as solvents. And I'll talk about the process, the Basel process that BASF have created in a few seconds as an example of ionic liquids actually being used in industry. So why are they so useful? Well, there's various different aspects that make them very useful. Firstly, they're not volatile. So you have an ionic liquid in a bowl and it will just stay there in the bowl. It won't evaporate. You can come back in 100 years' time, it's still going to be there in the bowl. This is in many ways very useful. We'll go on to some of the advantages and disadvantages shortly. It's also got a very high thermal stability. You can heat them up to 200, 300 degrees in many cases, and they are perfectly stable. They do not decompose or evaporate. They have a very high polarity and high density, which can be useful. They can also conduct electricity, for example. And they have a large liquid range so that you can heat them over a large temperature. They remain liquids. Obviously, if you cool them down, there is a point at which they will start to become a solid. So that's, they're less suitable for perhaps using at lower temperature applications. But above room temperature, there is no issue. They are, generally speaking, chemically inert. So it depends on how you design them, but they can be innocent in your reaction. They can just be there as a solvent rather than as a chemically reactive component, but that will also depend on the design. And then you can change how hydrophilic they are depending on the structure that you use. The synthetic aspects are very, very important. We're a synthetics research group, so it's important to be able to know how to make these ionic liquids. I won't go into that today, but it's a very well-established procedure, and you can modify these ionic liquids in many different ways to be able to get the functionality that you need. And they're relatively widely available as well, so it can be sourced readily. So there are some aspects written in red here. So very high viscosity compared to most solvents, difficult to recover sometimes and clean up, remove the contaminants. after a reaction, for example, and they're often considered to be quite expensive, and maybe they're also toxic depending on the iron liquid that you choose. However, of course, many of these aspects are also an issue with conventional solvents. So there's just some examples here of some of the typical parameters for an iron liquid. This is one that is shown down here in the bottom right-hand corner. It's a very cheap iron liquid. It's a mixture of triethylamine and sulfuric acid to give this iron liquid here, where you have protonated ammonium ion, and we have something that is very, very, very thermally stable and a high density, but is also liquid over a large range, so even down to -50 degrees centigrade. And it can also have variable hydrophilicity, and like many of its cheaper alternatives, it can be sourced from relatively widely available starting materials, such as the ones mentioned here: sulfuric acid, alkylamines, and acetic acid, for example. So one of the big issues is that these iron liquids are often very, very viscous, and that can make it quite challenging to work with. But it depends on whether they are used on their own or whether they're mixed with other solvents, and this is something that one can modify by using mixtures with conventional solvents. Recovery, as I mentioned, is difficult in many cases because they are so involatile. It does allow you to remove more volatile components from the iron liquids by distillation, but this is an energy-intensive process, and you then have to use other methods for less volatile compounds, such as supercritical extraction, liquid-liquid extraction, for example, and trying to crystallize, trying to get your product out of an iron liquid can sometimes be difficult because of their ability as solvents to be able to keep many different species in solution, which is an advantage in some ways. It can also be a disadvantage. One thing I think also people don't often appreciate is that iron liquids are heterogeneous on a nanoscale. So it means that you have a bulk solution, which is pretty uniform. But when you look down at on the nanoscale, you start to realize there are domains within the liquid that are perhaps more hydrophobic or hydrophilic, and that you can end up having slightly different behavior depending where you look in your solution. And this is something that's been investigated, and in particular the length of the alkyl chains in the iron liquids plays a big role on the size and the connectivity of these domains. And it's something worth bearing in mind. It's not something that's we found to be an issue, but it's actually something that people are trying to exploit now a bit more in terms of the potential applications of iron liquids. So people often say, well, iron liquids, aren't they very, very expensive? Well, they can be, certainly, if you use iron liquids such as this one here, which is often called BIMIM PF6. That's expensive. 1,500 euros per kilo is pretty expensive, and you can buy it on a 250 gram scale. But we don't use that. We use perhaps some ones that are a little bit similar, but certainly a lot cheaper than that. But if you go down to the other end of the spectrum, in terms of price, we have a number of examples here which are very, very, very inexpensive. And there's one here at the bottom, which I showed earlier, which is around €1 per kilo. It's not created on a very, very large scale, but if it were, then it would certainly be even cheaper than that. So certainly the idea that they are expensive is not necessarily the case. I think that one has to bear that in mind when one's designing the experiment, and whether one is going to try and reuse the iron liquid, which is of course what we should be doing in terms of sustainability. But it is something that where the cost aspect is not necessarily as prominent as people sometimes think. So are they green solvents? Well, that is a good question. And I would say probably the answer to cut to the chase is that they can be green solvents. I mean, they have certain very important benefits. They don't evaporate, as I mentioned before, so you don't have to have the same sort of control measures to stop volatile solvents escaping. And so they don't have this atmospheric photochemistry, so therefore you just simply have the liquid and negligible vapor pressure, but they don't evaporate under normal conditions. This allows you to do a lot more within environments that don't have such strict control measures for that you would use for volatile organic solvents. And this allows you to avoid exposure, for example, to these solvents by the people using them. But this, of course, is also a drawback. So if you spill some iron liquid in the corner of the room, it will still be there in 100 years' time. It's not going to just evaporate and disperse as would be the case with a normal solvent. And so therefore removing it, but requires processes that can be energy intensive, like washing, absorption. And of course, they are salts, so they are often miscible with water and can enter the drinking water sources, which is obviously also something one has to bear in mind. So the toxicity of iron liquids will obviously depend on the constituent components, but they have potential to cause great harm as a result of the toxic anions that are sometimes used. So there is a move now to use biocompatible iron liquids, ones that are often made from amino acids, for example, so from a natural source. And there are some examples just shown down here below, which are now commonly being used, such as choline chloride and acetic acid. And this last one here, emium acetate, is classified as harmless by the legislation that governs the hazards of chemicals. So I think that it's quite clear that iron liquids can be used responsibly as green solvents, but one has to bear this in mind when one designs the process. So they are used in industry. They're currently used in a number of major processes. And it's interesting to know why they have been adopted. So they are, because they are tunable, you can then use iron liquids in lots of different ways. And some of the solutions they've delivered have led to production problems being solved, such as in the battle process I'll show you shortly, and also new reactivity. So they actually give different products with the same reaction in the iron liquid medium compared to organic solvents. Often you can get an improved reactivity and greater productivity for your process using iron liquids. And importantly, it should be recognized that they do provide the option for viable processes to be created using this solvent class. It's no longer something that's just a lab curiosity, it's something that is being used in industry. And many of the examples shown above are protic iron liquids, so ones which have protons, which can therefore be weakly acidic if required, or more strongly acidic if also required. However, despite all of this, there's still a lot to be uncovered about the behavior of iron liquids, especially mixtures of iron liquids, and that's something that we're also interested in. So the Basel process is one that I've mentioned a number of times now. It's this process here to make alkoxyphenyl phosphines, which is these compounds over here. And this is done through the reaction of dichlorophosphines with alcohols. And it was found that in the presence of methylamidazole here, this reaction is improved hugely. And the reason partly for this is that this forms an iron liquid, because this in this process here, chloride ions are produced. They then form an iron liquid with methylamidazole, which is this compound here. This is the iron liquid, and that then can be recycled through the use of base to regenerate the methylamidazole, which acts as a proton sponge, as they call it. It mops up the protons that are and the chlorides that is produced in this reaction. But it can be recycled, and in fact they found that the presence of this iron liquid in the process actually speeded up the process dramatically, allowing a huge improvement, as shown here, in terms of productivity, which then in turn allowed the whole process to be done in a flow manner. So using a small reactor as shown here, which can be held in the palm of your hand, to be able to create a huge amount of these alkoxyphenylphosphine products in a very efficient process. Also very important for anyone working in industry particularly is the ease of separation of the product, and the fact that this forms, that the methylamidazole, when protonated, forms this iron liquid, leads to 2 different phases. So it's very easy to separate this product here from the iron liquid that's formed, and so makes the whole process much more straightforward. And so as a result, it reduces production costs, creates less waste, uses less energy, so very much a sustainable process. So why should we use iron liquids for biomass in particular? Well, one of the big advantages of iron liquids is that it breaks down and dissolves components of biomass. And this is not so straightforward. Relatively few, at least benign chemicals can do this. You often have to use very acidic solutions to be able to do this process otherwise. And also you don't get the processability of the different components in other processes. So if we take lignocellulosic biomass, as I mentioned before, we have the lignin, cellulose and hemicellulose. Using iron liquids and water, we can then separate them out, break apart the wall of the plant. The lignin components is separated then from the cellulose and hemicellulose, and then they can be separated out into the different fractions. And depending on the design of your iron liquid, you can then precipitate them in different steps, so that you can then take the biomass and separate out the various different components, and then use those individual components for making biofuels or for making platform chemicals, as I'll be talking about today. So we talk about refineries, petrochemical refineries. They're obviously something that we all are very aware of for processing the oil that comes out of the ground, it's extracted from the ground. And the idea would be to create biorefineries as an alternative. So they would be using biomass as the feedstock rather than oil, and they would then produce lots of different products which could be used for different applications. And that's something that is a holy grail really for researchers working in this field, to have biorefineries which can be located all around the world, wherever the biomass is, to be able to process the biomass and separate it out into the different components. And many of these ideas use iron liquids as part of their design. And this is because, as I mentioned before, iron liquids dissolve and allow pre-treatment of biomass, in particular that dissolves cellulose, which is something that's very, very difficult to do using other solvents, at least in an environmentally beneficial manner. So they've been used in many different aspects of the biorefinery: pre-treatment of the biomass, separating out the biomass, and then converting the various different components, in particular cellulose, to chemicals or to biofuels, but also lignin as well, which is something, as I mentioned, is very useful for carbon fibers. For example, building the structures that we need, very light structures such as for cars, currently use a lot of carbon fiber. And if that can be sourced instead from petrochemicals, instead from biomass, that would be very, very useful. And lignin is the most obvious component for that. Okay, so here is a little scheme. Hopefully you'll be familiar with some of these components. So if you take our biomass as shown here, and we treat it in some way, very, very possibly using iron liquids, we can then separate out the cellulose. And then the challenge is to move from the cellulose to glucose to fructose, and then, as I'll be talking about today, to various platform chemicals. And one that is going to be spoken about a lot today is 5-hydroxymethylfurfural, which is this compound here, or HMF for short. Now, this is a platform chemical, and it's been identified by the US Department of Energy as a leading platform chemical. And this is a building block which we can use for many, many different things, including plastics, which I'll show you in a later slide. It can also be used to create biofuels. For example, this 2,5-dimethyl furan is a biofuel which has a much higher energy density than ethanol, for example, and also doesn't suffer the same problems that ethanol has with water content. But at the moment, the issue is how to do this process, how to be able to reduce the HMF to make the 2,5-dimethyl furan in a way that is economically feasible, which I think at the moment has not been achieved. But this is one subject that people are working on, and likewise the conversion of 5-hydroxymethyl furfural to various different useful building blocks is something that is a very, very intense area of research, and something that I'll be speaking about today. And the topics I'll be speaking about are indicated in these green and red boxes. So the green box here is something that I'm going to show you in the next few slides. And the red box here is something that I'll talk about a bit later, in particular DFF and FDCA, which I'll introduce at a later point. Okay, so where did all of this research start? Well, I think it's fair to say that this publication by Zhao in Science in 2007 really kicked things off in the field. So these researchers showed that chloride-based iron liquids could achieve 70% HMF yield at 120 degrees after 3 hours using a chromium catalyst. And this is here is fructose, which can then be converted to HMF. And that was a major breakthrough because of the ease with which iron liquids can be used for the pre-treatment of biomass. It was very tempting to think that we could use the same solvent for pre-treating the biomass, separating out the cellulose, and then perhaps doing the subsequent transformations all in the same medium to be able to get our platform chemical out in the end. I'll explain some of the issues with that later on. So we recognized that while this was a very important result, the chloride, which is part of the iron liquid here, is also a good ligand and could bind the chromium and inhibit the catalysis, in fact. And so we decided to look at iron liquids which didn't, or one example of an iron liquid which didn't contain that chloride, and instead had the hydrogen sulfate anion here, which is non-coordinating, so it doesn't attach itself to the metal, in contrast to the other chloride examples which do. So we screened these three together to see which one would work best, and we found that the breakdown of fructose we already knew was favored by acidic conditions, but in particular when we use a mild acid such as the iron liquid itself, with the hydrogen sulfate anion, where they have a proton which is weakly acidic, allows us to reach a sweet spot where we have the right amount of acidity in the process to be able to do the transformation from fructose to HMF, but avoid the formation of byproducts that can be caused by strongly acidic conditions. And I don't want to show you lots of results, but just to highlight some shown here, we realized that the chromium catalysts were the most favorable, and this is indeed what Zhao had found out earlier. But we did some additional work on looking at adding water to the solution, and looking at different conditions, and essentially optimizing the process, but using our new medium of the hydrogen sulfate iron liquid, which was found to essentially create or to deliver almost quantitative, so pretty close to 100% yield of HMF from fructose over relatively short reaction times. Looking at all these different other metals that we screened for the process, we realized that it wasn't just a simple Lewis acid effect. There are many Lewis acids down here which don't perform very well at all. And so there was something about the chromium in particular that that led to a very successful reaction. The other thing that we discovered that it was also very, very selective as well. And so it created HMF without the attendant byproducts that many other processes experience. And that is a very important process, part of the process as well, and selectivity as well as just the yield of the desired product. And so we see here under the conditions shown here, we have 96% of HMF formed after 3 hours. So how does this chromium interact with the fructose? Well, it's suggested this is the mechanism. This is from other people's research. We have the fructose here in the cyclic form. It can be opened up by the chromium, which then coordinates to 2 of the oxygens, and this then allows the loss of water sequentially to form HMF through with an alternative, open chain species, which is in equilibrium with the chromium here. So this is what's believed to happen, and certainly it's borne out by our studies that a mechanism like this seems plausible. So it seems that the key aspects that we uncovered here was that using slightly acidic iron liquids allowed this process to be carried out very effectively, with all the attendant benefits of iron liquids, but also the fact that it's a weakly coordinating anion in the iron liquid, the hydrogen sulfate anion, was an important aspect. And so this near quantitative conversion of fructose to the platform chemical HMF is an important development. I mean, this research was done in 2014, 2013, a number of years ago, and there's obviously been a lot more work in the field since then. But it's something that really illustrated that you could have very, very, very high, very selective yields of HMF from sugars, and the relatively low loadings of chromium-3 chloride was also a benefit. People often look at chromium and think chromium is very toxic. Well, yes, it can be. So if you look at chromium-6, oxidation state 6, that is very, very toxic indeed, but chromium-3 is actually a lot less toxic. I mean, there are very few things that are completely non-toxic. So chromium-3 chloride is at the lower end of the spectrum of toxicity, and so it's not something that is that there should be a cause for concern simply because it features chromium as the metal. I think it's a mistake that people often make. We also didn't see any side products such as levulinic acid, formic acid, or humins, and that's a very, very important aspect for a biorefinery. You don't want to be creating lots of side products that then have to be separated from the process. And I think I mentioned humins there. It's something that people are maybe not so familiar with. Humins are condensation products. They're when the HMF reacts with itself to form polymeric or oligomeric material, or with the sugars that that are the starting material used in the reaction. And these are very complicated structures, lots of different variations in the structures. I'll talk about them a little bit later. They're generally something to be avoided if possible, because it is reducing the yield and it also causes a separation problem. And so overall, what we discovered is produced allowed a process with shorter reaction times and higher yields than previous work at similar temperatures. However, a metal-free alternative, of course, would be better. We've just mentioned about chromium. It's not so toxic, but nonetheless, one should be aware of this. And so in our more recent work, so just from a few years ago, we looked at actually just using a metal-free process with acidic, with simply acids like hydrochloric acid, HCl. And this is something obviously that would be more amenable to a scale-up of the process if we can try and avoid the use of metals. And in this, we discovered that a triflate anion, such as shown here, this is triflate, was ideal for this process. It is non-coordinating again, so it doesn't interact unfavorably in the reaction, but provides a medium for this dehydration reaction of fructose to HMF to occur. In particular, we found that the stability of the HMF in the medium was very, very important. So HMF is generally not the most stable compound, and it can often form side products like the humans that I just mentioned. And especially when you heat a solution which contains a large amount of HMF in it, it can cause those side products to form. And so we investigated the stability of HMF with different water content, because we suspected that because water is produced in the reaction, it's a dehydration reaction, that this may be important. And we actually discovered, as can be shown, as we've seen here on the right, that when you have essentially no water in there, we get a very high degree of conversion of the HMF to human side products, in other words, degradation of our desired product. But then when we increase the water content, we end up reaching a point where with 2 to 3% water, we get a much lower degree of degradation and reaction to these undesired side products. And that's a very important finding. And it's something that could allow us to stabilize the HMF that's formed, because of course your process is converting your fructose to the HMF, and there's still going to be a substantial amount of both of those components present during the course of your reaction. So that is an important finding, that a little bit of water is actually helpful. And we think this is probably through hydrogen bonding of water to the HMF and stabilization of that, of the product in the medium when a small amount of water is present. Another thing we also needed to discover is whether we could do this with high substrate loading. So a lot of people do these reactions, but using only a very small amount of their starting material, and so that's fine for academic purposes. But if you're going to scale it up on an industrial scale, you want to be using a very high loading, in other words, a very high amount of your feedstock in your solvent to be able to make it efficient, rather than having to have huge amounts of solvent just to be able to convert only a small amount of your starting material to your product. And this is something that we found was an issue. We can see here on the right here that the yield of HMF drops from 86% to around 72% as you go from 4 to 14% loading by weight of fructose in the iron liquid. This is likely due to the amount of water that's then being produced. You obviously get a much higher amount of water because of the dehydration nature of the reaction, but also perhaps other interactions that are going on at higher concentration, interactions between the molecules of the starting material as well. And so for a scale up of this process, it's been very important. I have a hand up there.
I'm sorry, Dr. Wilton.
Just thinking about the time.
To interrupt. Yes, I'm terribly sorry, but to interrupt your interesting talk, however, we only have 10 more minutes to finish the talk, sir. Sorry.
Yes. That's quite all right.
We're going to have another, yes. And then we're going to have another, we're going to have a Q&A session right after this.
Sure, absolutely.
So, yeah.
No, I'll
Sorry,
be aware of that. That's okay.
Okay.
Thank you.
Thank you.
Okay, so so yes, the process does require us to be able to solve this problem of being able to use higher loadings. But one of the things that we did discover was that we could do this reaction very quickly, and so we can then have a reaction which is complete essentially complete in only around 6 minutes. And this is something that's very important in terms of scale up. If you can do a reaction very fast, that means that you can then you can avoid many of the problems associated with the stability of your product in the liquid medium. Okay, so just to summarize on this point, that we're able to then obtain very high yields of HMF, a very important platform chemical, in relatively high fructose loadings. At 10% is where we got to in short reaction times. And so our optimum conditions were 10 minutes at 10% loading. And so this is something that that we are now taking forward. We're looking to try and scale this up, and in particular, this aspect of the water present is very important. Okay, so we would like to be able to use glucose instead of fructose, and this is something that that we are investigating and have done for a number of years. It's a more challenging substrate, but we can also create our HMF here from glucose via fructose. And this then moves us back towards pure biomass rather than having to use more processed versions of biomass. And of course, ideally, we would like to use cellulose itself, and that's something we have looked at, but it's a much more challenging substrate. One of the big issues is that cellulose is not very soluble at all. It's much better in terms of solubility in iron liquids, but still you're not able to pack a large amount of cellulose feedstock into your solution to be able to convert it to HMF. But that is something that we're also working towards at the moment. It's around 58%, just short of 60% yields using this process from cellulose. But this represents much less refined version of biomass, one that is much closer to the biomass that is the ultimate feedstock for these reactions. In the very last few minutes, I'm just going to talk about the other forward reactions. So we've got shown already here that we can go from cellulose, glucose, and fructose to the HMF, but then can we go to these other platform chemicals that are really, really important to be able to create the chemical world in which we live? So these higher value platform chemicals are often based on the route to FDCA, which is furan dicarboxylic acid, which is something I know that members of the audience are interested in. And so I'm just going to show you a little bit about how we can do this to try and get to FDCA. So one of the reactions that we need to look at is the conversion of HMF here to the diformyl furan, which is this compound here, which is an intermediate on the way to FDCA, and it's one which is also in itself very, very useful. A dialdehyde like this could be used in polymers, for example. And so we discovered that we could use TEMPO as a radical catalyst. Is TEMPO here, which allows us to convert HMF to diformyl furan. And we got some quite good results for this, up to 70%, 80% yield at 80 degrees centigrade. But one of the issues that we had with TEMPO, which is necessary for the reaction to take place, is that it's very volatile, and it's something that that is then lost from the reaction under the reaction temperatures at 80 degrees centigrade. So we needed a solution that would keep the TEMPO in reaction. And the way we did this was by actually incorporating the TEMPO as part of the ionic liquid itself. And then if we are able to take the base that we use and make that part of the ionic liquid as well, we have two components which are both part of the involatile ionic liquid medium. And this allows us to do this reaction, as shown here, to go from HMF to DFF at very high loadings, 40%, and then crucially to then sublime this product. So in other words, you heat it, and then the crystals of DFF, as you can see here, form on the side of the glass. And this allows us to separate it much more easily, and also to reuse the process a number of times. We can see that we reused it 3 times here to get full acceptable yields after the 3rd run. This is probably due to the copper catalyst that's used being deactivated. So it's an unusual approach. And so really just the last couple of slides, I wanted to show the overarching approach that we are now proceeding with in our current research, and that is to try and go to FDCA, which I just mentioned, which then can be used and converted into this polymer PEF, which is a very, very important alternative to PET or PET, which is the plastic that you probably have in if you drink Coca-Cola, you're probably drinking it from a PET bottle. So that's obviously petrochemically sourced. If we can replace that with something which is sourced from biomass, then we have the possibility of replacing the plastics that we use both for clothing and also packaging with a completely bio-derived source, which comes from biomass and ultimately carbon dioxide in the atmosphere. There are lots of problems with this at the moment, and that's why it's still not been commercially scaled up. But we've done some work on looking at what aspects, in particular the solvent choice, could be important in making FDCA production a reality. And I won't really talk about this in much detail, but we should also in a biorefinery think about using the side products that are formed, such as the humins, as mentioned earlier. And that's something we've looked at for removal of heavy metal waste, such as antimony from water supplies. So really nothing should be lost and disposed of. It should be, a use should be found for everything that comes out of the biorefinery ideally. So I think this is where I'm just going to finish with a summary that we've just discussed that iron liquids have excellent properties of separation of biomass, but also they're very effective media for the onward transformation of the fructose, glucose, and cellulose that comes from biomass to make platform chemicals, and it avoids the byproducts that are often a problem in these processes. We can also make a very, very rapid process that is suitable for scale up, and we can also then look at making other platform chemicals such as DFF from the HMF, and this is something that we're now taking on to be able to make FDCA, which is the monomer that underpins this green plastic PEF, which I'm sure you'll hear much more about in the future. So I haven't got time to talk about the very last topic. It wasn't many slides, so I'd just like to cut to the acknowledgements. I couldn't have done all this work, of course, without the people who actually did the work in the lab, and these are the people shown here. In particular, I'd like to mention Khairul Anwar Jantan, who is a Malaysian student who's received his PhD with us and is actually coming back to continue work on the recovery of metals project actually next month. And these are the people I work with, principally Jason Hallett in chemical engineering, who is the collaborator with whom I did all this work. And lastly, I'd like to thank you very much for your attention. I'd be happy to answer any questions.
Right. Thank you so much, Dr. Wilton-Eli. So far, we have 7 questions from the chat and the Q&A. Unfortunately, due to the time constraint, I think we can only answer a few questions.
Yes, apologies for that.
Yes,
my
apologies for that. It's all right. So maybe we could choose the first question from the chat section. The first question from Maegala Nallapan. So she asked, replacing chemical catalysts with biocatalysts, is it a viable move for mass conversion of biomass to useful products? Dr.
Absolutely. I very much agree that biocatalysts, enzymes, of course, are very, very useful. The only problem that you have with them is they are relatively slow and you have to use pretty mild conditions because you don't want to destroy the enzymes. So it's definitely being used, and in fact that's the big alternative to using chemical catalysts, metal catalysts, for example. So yes, that is definitely being explored. I think I see it more as a sort of parallel technology. It's not one that necessarily we have to compete with. I think some parts of the process work very well with enzymes, and some parts of the process work very well with metal catalysts, for example.
Thank you. We actually have 2 questions from people from non-science people, but perhaps I could just choose one.
Yes.
This one here is from Nurhasbi Abdul Samad. So the question goes, as someone in accountancy background, I'm interested to know, is there a significant financial benefit for industry to use iconic liquid technology? Dr. Wilton.
Yes, indeed. I mean, liquids, I think, have many benefits, as I've shown, and also the cost is not prohibitive. I think the crucial part about them, I mean, the liquids we used are the more expensive ones, it's true, and so we would perhaps need to design our process to work with cheaper ones. But I think the key point is they have to be recycled, really, and that's one of the things that people often don't talk about. If you can recycle them and reuse them, that is obviously much more sustainable, but it's also going to be much more important. Make the process actually feasible economically. And so I think that for an accountant, obviously it's very important to make sure that this is also an economic process. And I think that iron liquids there's enough evidence now that they can be used on a large scale, especially with the processes I've just mentioned, and they are economically viable options. Yes.
All right, so the rest of you, thank you for the questions. There are a few more questions for those of you who wants to to know more about what Dr. Ellie mentioned, Dr. Wilson mentioned just now, you could just perhaps contact Dr. Wilson personally after
Please do,
the
yes.
session. Yes. Dr. Wilson Ellie, thank you so much for sharing with us today. And I'm really sorry to cut you in the middle of
No. It's
now.
my pleasure, and I'm apologies that I ran on a little bit longer than expected. I sometimes get a bit, caught up in my presentation and didn't realize the time. So thank you very much for drawing your attention, for my attention.
All right. I've just gotten someone just they have a special request, maybe that you could, you could answer one more question, So yeah,
Certainly.
3 more questions. Yeah, so perhaps 3 more questions, Dr. Wilton. So perhaps the second, we will proceed with the third question. This is from Nur Shahira. So if I could read this for you. Hi, I'm asking as someone who is not from the science field, but if you could perhaps explain how big will iconic liquids can be in the future concerning various fields and markets to be involved.
I think that they'll become a standard alternative to the typical solvents to be used. I think people often underestimate the importance of solvents, and also the amount of how big an issue solvent loss is. So if you're using volatile solvents, they are lost. It's inevitable. You're going to have to spend a lot of energy recovering those solvents to try and make sure they're not lost. And if you have something such as ion liquids, which don't have a vapor pressure, which don't evaporate, then you don't have that issue that they're going to be lost into the atmosphere and all the associated problems with that. So I think they're going to become a standard alternative. I think in particular in electrochemical processes, which are becoming very, very popular. They are very, very, very good because they have a large electrochemical window, which means that you can do electrochemistry across a whole range of potentials. And I think that's something that a lot of people are interested in. So in battery technology as well, they're being used. So lots of different areas, people are starting to realize that the involatile nature of ion liquids and the various other properties they have are very, very beneficial, not least that the fact that they are tunable. So you can design them however you want. If you're using ethanol, it's always ethanol. It's always going to be ethanol. You can perhaps make it into methanol or propanol or something like that, but the options are limited, whereas with an ion liquid, you can just tweak it. You can tune it a little bit just to get the right properties that you need. So I think there will be important alternatives in the future.
All right, thank you. Perhaps I could read one more question from the Q&A right now. This is from Aisha binti Mutalib. So she asked a question here. Could you give some examples of suitable biomass in Asia for renewable feedstock? This is a question from Aisha Mutalib.
I'm afraid my knowledge is not sufficiently profound, I think, to be able to identify individual areas within Asia where biomass is particularly prominent in, for example, the energy sector or in platform chemicals. But I think one good example is looking at Brazil, for example. In Brazil now, routinely people will fill up with bioethanol at the petrol station, and this, the bioethanol that they fill their cars up with comes from crops that are converted into bioethanol. Unfortunately, quite a lot of that still comes from sugarcane, which has to be grown on good land. And I think the key point for Asia really is to identify land which is not suitable for crops, but you don't want to be competing with people's food crops, because otherwise you affect the poorest section of society disproportionately if you're pushing up the price of food. And so if you can identify the land which is not currently being used, but which could be used to grow very, very fast growing biomass, such as grasses and trees like willow, for example, those sort of areas which don't require very, very good land, but are still accessible to be able to be for a tractor or some other technology to be able to gather the biomass, then I think those areas are potentially very, very important. And many countries have large areas which are like that. And I'm sure that's the case in Asia as well.
Right, thank you. We have another 2 more questions. Perhaps I could repeat this one for you. Is this iconic liquid widely used in the industry now? Or is it mainly used based in Europe? If so, in your opinion, what can be done to ensure iconic liquid technology can be introduced in the Asian-based manufacturing industry? This is a question from Mumtaza Narobi.
Thank you. That's a very useful, very interesting question. Yes, I mean, I think that the technology is probably used mainly in Europe and in the US at the moment with liquids. But I think that the problem is that existing technologies are always about 10, 20, 30, 40 years old. So when you design a huge chemical plant, that's, it has to run for many years to make it viable. And it's very difficult to retrofit a plant with a completely new technology such as iron liquids. So I think that it would depend on the plant being created new. So, to meet a new demand. And I think that that's something that's really perhaps the drawback at the moment. People who are running the established plants don't consider iron liquids because that's something that is not compatible with their current system. But of course, as we move forward, and I think in particular with biomass, we're going to have small scale transformation of biomass into biofuels and platform chemicals, not massive plants probably. We'll have smaller local ones probably. Then I think that iron liquids have a much greater possibility of being employed on that scale, and that can then happen all across the world. And I think that that's the thing I mentioned right at the beginning. Biomass is very widely and fairly evenly distributed around the world. As long as you have some land, you can grow plants which can then be used for biomass. So I think that iron liquids will become a very important option for people when they're designing the next generation of facilities to transform biomass into the useful chemicals we need.
Thank you very much. And finally, the last question from Nur Ashikin binti Muhammad. The question goes: the switch from existing approach to liquid technology requires strong political will, something Malaysia needs to learn from others. How did countries of your study do this? That's the question.
I mean, I think that though there is definitely a role in encouraging adoption of these technologies, by the governments in the various countries. I think that so far most of it's been done on an economic basis. For example, BASF is a very large German chemical company or international company based in Germany. They used iron liquids because it was better for their process, that it ultimately made their process much more able to do on a much larger scale and to produce a much larger amount of their product at a cheaper cost. So I think that's an economic incentive that any country, companies in any country will be able to pursue. However, I think where the governments can really help with these things is to support research in universities, indeed, of course, like yours, where in places where biomass is prevalent, such as in Malaysia. So I think that the support from the government in research will then start to trickle down into the economic activities of companies. And so I think that that's rather than having a law that means that iron liquids should be adopted wherever possible. I think it's much better to encourage research into it and make it clear that this is both an economic incentive as well as an environmental one.
All right, I think that's all the time that we have for today. Dr. Wilson Neely, thank you so much for sharing with us today. Thank you once again.
Thank you. It's my pleasure. Thank you very much indeed.
Right. We shall have a 5-minute break, and when we come back, we will continue with the forum session with the panelists. Until then, ladies and gentlemen, thank you so much. We'll see you in another 5 minutes' time. Ladies and gentlemen, to i-ConSPADU 2021. Just now we had a wonderful session with our keynote speaker, Dr. James Wilton Eadie of Imperial College London. We shall now proceed with our next agenda, and with that I shall pass the floor to our moderator, Nur Shahira, to facilitate the forum session on great sustainability challenges the world needs to be prepared with. Ms. Nur Shahira, are you there?
Yes, I'm here.
All right. I hope the panelists are ready. So if you're ready, Noshahira, the floor is yours.
Thank you very much, Mr. Grace. So first, let me just check whether our panels are all here. Is Dr. Thomas here? Oh yeah, I can see you. I can see him. And let me just check. And there's Dr. Amjad and also, all right. So all our panels are here. It's a good day, everyone. Assalamualaikum and a very good afternoon. It's afternoon in Malaysia. So welcome to the International Conference on Sustainable Practices, Development and Urbanization, i-ConSPADU 2021. First, let me introduce myself. My name is Nurshahira Azman, a lecturer from the Center for Foundation and General Studies, UNISEL. You can call me Miss Shahira. Today, I will be your moderator for this session. But before we start, let me introduce our amazing panels for today. I'm glad to welcome Dr. Thomas Weinberger, the co-founder and managing partner, head of R&D, Stirtec, Austria, and the lecturer of Graz University of Technology, Austria. He was born in Wales, Upper Austria. Our first panel here is a major in mechanical or industrial engineering sustainability. Besides his great number of publications, he also received an Inventor of the Year award from Graz University of Technology, Austria. Welcome aboard, Dr. Thomas Weinberger. Thank you so much for being on the panel today, Dr. Thomas.
Hello, good afternoon from Austria.
Good afternoon. Okay, now next for our second panel, we would like to welcome Dr. Amjad and Hussain. He was born and raised in Norway. He later traveled to the United Kingdom, where he completed his A-levels and higher education, including his doctorate. He went on to work as a lecturer in religious studies at Trinity University College, Carmarthen, and later as a senior lecturer in Islamic studies at Trinity St. David, University of Wales, United Kingdom. He's currently an associate professor in the Faculty of Divinity at Marmara University, Istanbul, Turkey. He has also written numerous book chapters and journal articles that have been published in the United Kingdom, United States, Malaysia, Pakistan, and Turkey. Thank you very much, Dr. Amjad, for being the panel for today. And next, our third panel, Dr. Amir Shaharuddin, is currently the Chief Executive Officer at Yayasan Waqaf, Malaysia. He is also the Dean of the Center for Graduate Studies and the Dean of the Faculty of Economics and Muamalat, University Science Islam Malaysia, USIM. Associate Professor Dr. Amir obtained a PhD in Arabic and Islamic Studies from the University of Exeter, United Kingdom, and a Master of Business Administration with honors from the International Islamic University of Malaysia. He graduated with the Bachelor of Arts with honors in Sharia from Al-Azhar University, Cairo, Egypt. Currently, he serves as the chairman of the Sharia Committee at Hong Leong MSIG Takaful and a member of the SC Hong Leong Islamic Bank. He also served as a member of the Sharia Committee of RHB Islamic Bank Berhad. Dr. Amir has authored numerous published articles, journals, and has also presented academic magazines at international conference. In addition, he is the first visiting fellow under Scholar in Residence, a joint initiative between the Securities Commission Malaysia, SC, and the Oxford Center for Islamic Studies, OCIS. He was also appointed as a visiting scholar at Urgent State University, Uzbekistan in January 2020. Thank you so much, Dr. Amir Shaharuddin, for being part of today's panel.
Thank you.
All right. So committed to responding to the needs and urges for anchoring awareness of sustainability in various aspects for the sake of longevity, we anticipate participants across the globe to share as much knowledge as they can in various fields with our panels today. So ladies and gentlemen, when we talk about sustainability, there is no universally agreed definition to it. There are so many different viewpoints and opinions on this concept, especially on how to achieve it. If you take from its root word, the word sustain means to give support to hold up, or to keep up. Sustainable means the capability of being continued at a certain level. The views on sustainability seem to have a stronger focus on the present moment and on keeping things above a certain level. So by its turn, sustainable development focuses more on a long-term vision. By adding the concept of development, Sustainable development means not only that humankind should satisfy its current needs without compromising the ability of future generations doing the same. Along with it also comes an idea of societal progress and an increase in quality of life across the globe. However, achieving sustainability isn't a piece of cake. It envelops many different roles, many different fields, and requires a great deal of commitment and responsibilities. Hence our topic today. We need to talk. Great sustainability challenges the world needs to be prepared with. Our panels today will be sharing their views with you on sustainability and the challenges to achieve it across different fields. So without further ado, let me invite Dr. Thomas Weinberger, the first panel, to share his presentation on the topic. You may share your presentation slide as well, Doctor.
Yes, thank you very much for the kind introduction, and also thank you very much for the organization committee for organizing this conference. So I think it's a very nice topic, and I'd like to share my thoughts today about the industrial production. So I think you heard about my background. So I'm in the more or less in the industrial production, and I want to focus today more or less on the transformation from the more or less conventional industry to new green processes, especially in the automotive industry. So can you see my slides? So I think
yes, we can see it clearly. Yeah.
So I want to start now with the talk. You can see here is the city of Graz. It's a very nice city inside of Austria, south of Austria. And here you can see a hybrid car, which is very nice for the development from the combustion engine to new concept. So there is the concept of the electric cars, we have the hybrid cars, and now also the hydrogen cars. And especially in Austria, where you have a lot of mountains and you have a few large cities, it's very important that you can maybe go from one city to another city without any problems. So in the cities, often you have the infrastructure to use the electric cars, but when you go from one city to another city, you need more or less the combustion engine. So there are new concepts developed that this will happen. And on the next slide, I will show you about the development of this technology in the automotive industry. So it's more or less a new concept where you use the batteries for the cars instead of the combustion engine. I've shown here a typical full electric vehicle. So the floor of the car is more or less made of all the batteries. The batteries are inside a battery tray, and in these batteries, you have typical capacity, and more or less for the full electric vehicles, it's maybe possible to use this car to achieve 450 or 500 kilometer, and for hybrid cars, maybe 100 kilometer, where you can drive with this electric vehicles. So, but what is the process development? So when you use the cars, maybe you think it's a very green car and you have no CO2 emissions, it works quite well. And especially when you come to the production, then you have to care about all the production processes. And what you can see here, I've highlighted that during the production process, often most of the CO2 emissions occur. You see that the development or the manufacturing of this typical car produce a little bit more CO2 emissions than a conventional combustion car. So, but during the process, when you use maybe green energy, then it's possible to reduce about the whole lifetime of the car, the CO2 emissions, and maybe have a really green car. In some areas, maybe in Norway, for example, where it's possible to use a lot of renewable energy, it's a really low CO2 emission. But when you compare it to another countries where they produce the energy with coal or gas, then maybe it's not really a green use of this car. So it's not only the use, but it's also the manufacturing process for these cars. I've also shown here a slide about the use of material. So we have to care also about the natural resources, and especially for the electric cars, there are many different components which are critical in the car. I'm sorry, it's in German, but you can see here on the top, it's carrosserie means the body structure. It's more or less made from aluminum and steel. Then we have the electric motor from copper and maybe rare earth materials. And then you can see on the blue part is the battery. And especially the battery has the disadvantage that you have many elements and maybe some critical elements. One critical element is lithium, and another critical element is cobalt. So why is cobalt critical in the industrial production or for the sustainability of the cars? You can see here 8 kilograms, for example, this is a medium electric vehicle where they use 8 kilograms of copper for one car. And this copper, also the mining of the copper is very energy intensive, and the conditions in Africa where many of this copper exists are very critical, and also the work is quite heavy. So you can see there are many mines where small mines, often it's very dirty. They have to take their hands and only small tools to go to these mines, and often our children are working in these mines. So it's not a real sustainable use of the copper for these electric cars, and especially with many cars, you can imagine how many cobalt we have to implement, and how many copper we need cobalt we need for this electric vehicles. So I think the major thing in the development of new electric cars is not only that we extend the range of the cars, so especially maybe you want to use the car for 800 kilometers instead of 400 kilometers, but also it's important that the industry develops new battery packs with less cobalt, and there are new tendencies that cobalt is also an important part during the manufacturing process of many other parts. So there are batteries are used also for many electronic components. So I think the reduction of the cobalt in the electric mobility is a very important factor for the sustainability. So I've here shown one slide from the TechWire magazine in Asia. They announced this year also that the future of the electric vehicles is cobalt-free. And also not only it's good for the natural resources, it's also very helpful to reduce the costs. So they said that with cobalt-free batteries, it's possible to reduce the cost by a third. Also, the major players in the industry like Tesla, they're working quite intensive to produce these batteries. And I think in a few years, we will have more or less really reduced amount of cobalt in the electric vehicles. And I think this will help also the sustainability and also the use of these cars in the industrial, as in the industry. The next slide is about another technology which is often used, or maybe is coming more and more important. It's about the use of hydrogen, not only in the use of the cars, but also for railway or for airplanes. So it becomes more and more important. But we also have to consider about the use of the hydrogen. Where do we produce it? How we produce it? And where do we need it? So we have to transport the hydrogen maybe from place A to place B. And this transport also needs energy, and also sometimes it's difficult to produce it as a green process. On the next slide, I've shown here the different manufacturing processes. So we have the conventional gray hydrogen. We produce the hydrogen from more or less the conventional dirty oil or natural gas coal, and we produce a lot of CO2 during this process. But the goal is to use in the future the green hydrogen. So especially with the renewable energies, wind and sun, it's possible to create CO2-free hydrogen. And also biomass is a very nice possibility to produce green hydrogen. Here you can see one picture from south of Graz in Austria. We have many sites where we produce the biomass, and especially from biogas, we can also create the hydrogen. There's at the moment at this site an installation where they achieved with the Graz University of Technology to produce the hydrogen from the biogas directly at the biogas plant. So you don't have to transfer it or to use additional energy to bring it to a biogas plant. So here you produce the energy locally, and this is very helpful also for the reduction of CO2, or also you can see here when you have to transfer it. We had a big project about development of new trucks or trailers. In this trailer, you can store only a limited amount of hydrogen, and with these trucks, often there are conventional trucks with combustion engines. They produce a lot of CO2 to bring hydrogen from place A to place B. So I think it's very important for the sustainability of this new technology that we can produce the hydrogen locally, and also to find new possibilities to transfer it from place A to B. Like there are existing pipelines in whole of Europe to transfer oil and gas, and some of these pipelines are also feasible to transport hydrogen. So I think this is also an important factor for the transformation from the old economy to the new green processes in the manufacturing. Here I've also shown about manufacturing of wind towers. Maybe some of you only think, okay, we produce green energy with wind towers. They are very friendly and you don't have some waste or emissions during the production of the energy. But there's a lot of energy needed during the manufacturing of these wind towers. And I've shown here about 14% of the energy, electric energy consumption is in the metalworking industry. So especially the development, the manufacturing of metal components needs 14% of the energy. So we always have to consider not only the life of the product, but also the manufacturing process when we talk about the sustainable processes. So when we see this, the sustainability is becoming more and more important in the industrial production, and especially during the manufacturing processes. Here I've also shown some parts that were made for the wind towers. You can see here the steel. First the steel is produced, then they put them together to big plates, and then they create this large platforms, or more or less a large base for the wind towers. And this needs a lot of energy. And in a study from Aso and Zhuang, they showed that the manufacturing is large part of the energy demand and CO2 emission during the development or the manufacturing process. So how do we produce such parts? So there, the welding is very essential. I think most of you know this picture. When you see a welder somewhere in the street or at the construction site, you have a lot of fumes, you have this radiation, and the welder is protected. He needs some gloves. He needs also a possibility that he doesn't get too much radiation. And so this typical welding is a very old technology, but it's also known as dirty, difficult, and dangerous. So during welding, this is, I think, a very important manufacturing process. We melt the material, so we heat it up, then it liquefies, and during solidification, you have a connection between the two parts. So this is, I think, very old. So the first welding parts, they were developed many thousand years ago when they tried to combine small parts to make tools, especially for example, in salt mines, where they tried to get the salt out of the mountains, and to get the tools, they found some iron, put them together, and made a bigger part. So it's always very interesting technology. But the conventional fusion welding, when you heat the material, it gets liquid, and often there is a big amount of toxic fumes and gases, also sometimes heat, noise, and radiation. And especially due to this radiation, there are high costs. The US estimated the cost, for example, about $500 million annually, about only the costs for treatment due to this special eye injuries. There are also big environmental problems during the process. So we have, for some of the processes, high CO2 emissions. We have high energy usage and emission of gases, fumes, and nanoparticles. So these nanoparticles are really very dangerous. They go into the lung and make very dangerous for the welder, but also for the people who work in the same area. For example, you have a manufacturing area where you produce the parts, and there is the possibility that this personnel which works there gets also ill due to the particles, and it's very important that you have to take care about this manufacturing process. So how can we make also the welding process during the manufacturing of parts more sustainable? So I think it's very important first to take care that the emissions should be minimized. So especially what we saw before, the amount of particles, also the radiation, dust, and so on. And also to reduce the amount of energy. And this is a possibility to get more sustainable during the manufacturing process, and also to reduce the energy consumption during the welding of different parts. So I've summarized here on the next slide the main issues during the welding process. How can we get it more sustainable? I think very important is the minimal material wastage. We use minimal resources. We also try to get cost savings for the customers. So maybe this is also an important factor when you consider the conventional fusion welding. When you are able to reduce the amount of emissions, you maybe don't need additional infrastructure to remove these particles from the air, for example, and this gets very expensive during the process, or to protect the welders and also your other workers from the radiation. So sometimes this is a very expensive part of the development when you have a new manufacturing site and you need a lot of infrastructure to protect your welders and also to remove the emissions from the air and also protect the environment from these toxic fumes. Also, we try to find processes with higher process efficiency, We also want to maximum the environmental benefits, and altogether, I think we can say these are sustainable welding processes. So what example, as I want to show today one example where we focus in our company in Austria. We use a special technology which is called friction stir welding. So this technology doesn't use a lot of energy. It reduces the energy, and it works like when you put your hands together and you create friction between your hands. When you do it faster, you create more friction and more heat. Or when you put them put more pressure between your hands and move it, also you create more friction, and it gets more, you produce more heat. So this is the main principle of this process. We have two plates, for example. We want to weld them together. We use an additional tool. I think it should start now. Okay, there's some issue with the video, but we press the tool inside the material. The tool rotates. We create friction. The material gets plastified, so it gets very soft. And with this tool, we also stir the material. So it we mix two materials, and then we move the tool along the joint line. At the end, we retract the tool, and we have a final joint. So this is a very nice technology, and especially during the development of components for the automotive industry, especially aluminum component, it gets very attractive. You can see here two examples. On the right side, we weld two parts together for a base plate in the automotive company. On the upper right side, there is the final weld. Here in the middle of the picture is the tool, and here is the remaining joint. So we move the tool along the joint line and create a very nice joint. Also on the left side, which you read here, we produce a gas tank for the transport of the hydrogen. The very beneficial is that due to this special process, we get very good properties in the joint, and we have no problems with hydrogen which goes through the weld. The process was developed in Cambridge in the United Kingdom, and first it was used for more or less the industry, especially for the tanks of aircrafts and for spaceships. But now we have more and more development in the automotive industry. I've here also summarized the advantages of the process. I think for today, I want to focus more on the sustainable process benefits and also on the energy. So we put less energy into the weld, so we get also less distortion of the parts. Also very beneficial is we use no filler material, since we have no liquefaction, so we weld in a solid state process. We produce no smoke, no welding spatter or other emissions, and therefore it's a very environmental friendly fabrication process. So when we compare, for example, then also the energy that we need for welding two parts together, we did a comparison for two different materials. I've here shown also some results from a study for aluminum welding, and you can see here we have 42% less energy compared to the conventional fusion welding process, which is a lot. And we also have 10% less material when we want to design the material for the special application. So for example, you need a special strength in the joint. And for example, in the car, that you have a crash safety component. And when you use this process, it's possible to reduce the thickness of the components, to reduce the weight of the component. And this is also beneficial for the later use of this process. Also, we can speak that this is a process where we reduce the greenhouse gas emissions by 31%. And in total, when we compare it to the slides which I showed before for the fusion welding process, we heard that it's a dirty, difficult, and dangerous technology. But with this technology, we are able to reduce the emissions, and we have a very safe, clean, and clever technology, and very competing with other processes. Here I've shown some early developments. First, it was used as discussed in the space industry, aviation industry, and now it's more and more used in e-mobility, for e-mobility applications. I want to skip this slide. So here you see a video for welding. This electronic box. The tool is now rotating. We plunge this tool into the material, create soft material, and we stir them together. And you see it's not very marketing friendly, so our colleagues always ask for some better pictures, because you see it's not really spectacular. You don't see anything. It's very simple. Now we finished the weld, so and also the weld appearance is quite nice. So I showed at the beginning a little bit about the hydrogen economy. So here we see also we have a big potential for the use of the technology in the hydrogen business, for the storage and transport of hydrogen, also for the fuel cell cars, and also for components which are necessary to transport the hydrogen from one place to the next. I want to show at the end of my presentation a few examples where we use this technology already in the industrial production. For example, at the beginning you saw this nice Jeep Wrangler picture in Graz. This is made, the battery for this Jeep Wrangler, the battery tray is made with the technology, with the friction stir welding technology, and was very successful implemented. And now we are in the serial production of these components. You see here the final components where we weld more of, I think, 15 pieces together to create one battery tray. Also, we have a lot of applications in the German automotive industry. For example, here for Daimler, they produce cars with hybrid and with full electric vehicles. And for example, this is a picture shown from the International Automotive Fair in Germany, where we also use our technology to weld the battery tray and also weld multiple parts together to create a nice final battery box. So here in this box, here are the batteries for the application, and in the front you can see the conventional combustion engine. So this is the hybrid concept, that we have a small battery which works for more or less 100 kilometers. Then I want to show at the end now also the cost comparison. So it's maybe interesting from the technology point that we use a process with less emissions, with very good quality. But what about the costs? It's always very important for the customers, since they want to reduce the cost during the production process. And I have here one example for full electric vehicles, where we see on the lower right side a typical machine that we produce for our customers. The price is approximately $1 million. And with this machine, you are able to weld big battery trays with about 2.5 meter by 1.5 meter, and this in very fast process, up to 5 meter welding speed per minute. When we compare then the costs of this technology with other technologies, I have here shown 3 different concepts. Also, one is friction stir welding, is the middle, and one very attractive process is also the laser welding process. It's a hybrid process with conventional fusion welding and laser welding. So we have the highest investment for the friction stir machine, but due to the fact that we can optimize the use of this technology, we are able to reduce the cost per meter, and we have the lowest cost per meter with this friction stir welding technology. So, for example, this is a car also for a German manufacturer. There are in total 22 meters of weld in one car. So when you use, for example, for the serial production with 200,000 cars with this amount of 22 meters, you need more machines, but in total, as I said, you're cheaper. And this comes to my final conclusion. This green and sustainable processes are not only beneficial for us as a manufacturer for this technology, it also provides the cost saving for our customers, and therefore we see a big increase of with very old buildings, and especially mid or end of November, we have these ice sculptures which are placed there. At the moment, we have very mild winter here, so maybe we have to wait a little bit. But I think this is a very nice design and shows that we also maybe should care about the environment, and maybe this will help us also to create less emissions and also to bring us to a more better future and greener surroundings. So I'd like to finish my talk. I think I'm quite in time, hopefully, and hopefully it was interesting for you, and I'm happy to answer any questions.
All right. Thank you very much, Dr. Thomas. That's actually very interesting. We are now realizing that sustainability is something important to practice, even in industries like car production, energy production, and even welding, to reduce the usage of, you mentioned about the inhuman labors and unsustainable ungreen practices. And also friction stir welding is what caught my attention, was that one point you mentioned, no smoke, welding spatter or other emissions. So I think that's when we mention about welding, that's the image that I see, all the spattering of fireworks, the smoke. So it's definitely a little bit unsafe if you don't have the safety gears and all. All right, that's a really interesting sharing. So now I'm looking at this list of questions that we have in the chat. So let me read one. This is from Dr. Maegala. Since Malaysia is blessed with natural resources and we actually export gas, the needs for hybrid cars are not urgent. In your opinion, Dr. Thomas, how do we motivate the change to hybrid cars in Malaysia?
So it's a very interesting question. I'm not sure about how we can use this hybrid cars. So therefore, I was also mentioning the different concept. So I think for when you only use the car in the city centers, maybe in Kuala Lumpur, maybe there is a lot of pollution there. And so maybe it's better to use full electric vehicles because you have the infrastructure there. But maybe when you go to another place in Malaysia where the infrastructure is not, maybe then it's better to use this hybrid cars. That's what I wanted to mention at the beginning, especially in Austria. I know much more the geographic specialities in Austria, where we have the mountains. It's the Alps between the north and the south parts. We have in the north, we have Vienna as a capital, is a large part, and then we have South Graz and some smaller cities, and also another big city in the north of Austria. So, for example, for delivery service and so on, it's very helpful to use this full electric vehicles, but when we often want to drive to other parts of Austria, maybe for skiing, then we have not the possibility to plug in and also to load this electric vehicle. So maybe then it's helpful to use this hybrid cars. So maybe this, as I said, I'm not very well, I don't know very well the infrastructure in Malaysia, but maybe this is an important factor that when you have not the possibility that you have enough energy, maybe then it's helpful to use this hybrid concept where you are also able to go green, maybe in the city center where you want to reduce the pollution, but outside of the city center, then maybe you can use the conventional combustion engine.
Yeah,
So maybe
that's definitely
hopefully
true. It's interesting you considered our we have the city, and then we have some parts where they're lack of not much, like maybe in the rural area, so it's hard to actually promote fully the hybrid cars usage. But yeah, we need to transform a lot of things first.
Yeah, of course.
All right. So allow me to pick one more question. It's quite relatable to the first one. It's from Ms. Mirza. We have constraint in terms of finance to go about with the sustainability ideas. So in your opinion, will we be able to overcome this in the near future, or will the non-renewable resources still be the cheaper option?
I think at the moment we see also the increase of the oil price again. So the oil price was down, and it was very attractive to use the conventional cars. But in the last weeks, also we saw in Europe some problems, and we see that gets more and more attractive, especially when it's possible to produce it by renewable energies. As I said, when you have the possibility, like in Norway with a lot of wind, or in Austria we have a lot of energy produced with the water turbines. So this gets then very attractive, and I think also that the cost goes down. And I think for hydrogen it will take some time, but in maybe 10-15 years, when we have enough possibilities to produce green hydrogen, then it gets more and more attractive also for the use in the industry. And also, for example, we have restrictions due to the politics, more or less. They agreed on different concepts. And maybe, for example, in Austria, we have now, they announced that they will charge additional amount of money when you use the conventional combustion engine. So for every fueling, you have to pay additional amount of money. And also, I think this is very important, that also not only the people want to go to green process and sustainable process, but also that you prepare everything that it gets more attractive for the people to use processes, also in terms of tax, and also in the to support also companies which produce this environmental friendly technology, to maybe that they get some funding also, and then it gets more and more attractive also for the use of the technology.
Yeah, it needs like reinforcement from every single party to make it possible.
Yeah.
Okay. Allow me to read this one question. So you mentioned about welding. So is this new welding technology, the friction stir welding, used in Asia? So is there any major challenges for Asian industry to apply this technology?
Yes, I know, for example, there is a lot of, so we have, I think the last slide where I've shown this big machine, this was a machine for the Korean market. So Korea is very strong in the development of this technology. For example, Hyundai, together with Samsung. Samsung is producing the batteries. Hyundai is using this for their cars. So they have very strong need now to use this technology. We see also in China, there are many sites which use this technology to produce trains and now it's coming more and more also for the cars, and also for consumer electrics. For example, Apple, this was very early application where they used this for the manufacturing of the iMacs. It's also a production site in China, and more. I think there's one university also in Malaysia, when I remember correctly. They use this process, but I'm not sure if there are any production sites in Malaysia which use the technology.
Oh, okay. We got to look into that, definitely.
Okay.
Yeah. I just because I'm not aware much about this because I'm from social sciences, so it's a very eye-opening topic today. And one last question. This from Azmi. May I know, where do EV batteries go to? Are they recycled in a sustainable way? So perhaps you have some answers to this.
So I'm not really the specialist for the battery itself. I know that they want to start now to really reuse these batteries, but I think there is a big issue that we maybe they don't know at the moment how to reuse it really in the right way, and also how to use it, since the capacity is maybe not so good. There were concepts to use it for example in the construction side or in rural areas to have some energy storage there. But yeah, as I said, I think there are many concepts, but yeah, I think there's additional need to make real good concept how to reuse these batteries.
Yeah, that's true. Okay, Ms. Aisha here, last one. Can you reveal any globally famous company which has collaborated with Stirtec for this technology, the friction stir welding? Would be interesting to know, actually.
So I can maybe mention for them in the railway industry, you know, maybe Siemens. They produce their some of their parts in Austria. So we developed the technology for applications, and they are already using the technology now in serial production. We're working together with Nemak, is the biggest supplier for cast aluminum worldwide. It's a company from Mexico, and they are more or less main supplier also for Daimler. I showed before the one battery tray for Daimler, where we produce this welding technology for Jeep Wrangler, where we also supplied the machines. And now we have also a project with Airbus. So I think it's also a big and maybe well-known company in the whole world.
Okay, all right. Thank you very much, Dr. Thomas. That's a very insightful sharing. Actually, audience can still ask questions in the Q&A option, so the panel can actually look at it and answer questions if you have more. So thank you very much, Dr. Thomas.
Thank you very much, yes.
And now let me invite our second panel, Dr. Amjad, to share his presentation for this topic.
I think my subject is very different. Let's see if I can share the PowerPoint presentation. Now, are you able to see this and hear me?
Yes.
Yeah, we can see it. Yeah, we can see the slide.
Okay, that's great. So I will start now then. I'll be speaking about Islamic education and contemporary theories on alternative holistic education. And so my topic is more about education and sustainability. It's about dealing with the background of how we should change our minds, how we should behave towards the environment, and so on. And so, first of all, maybe what I should be saying is good morning from Istanbul and good afternoon. I think it is in Selangor and Malaysia. Thank you for inviting me to this international conference on sustainable practices, development and urbanization, 2021. Again, also a gracious acknowledgement and thank you to those who have organized this conference. Now, as I said, this paper is about comparing contemporary education with holistic education and possibly looking at Islamic education as something comparative or something that could be suitable for educating about not only the environment, but for the whole person. So holistic education, it's the holistic outlook, speaks about, it's about education and looking at the person as a whole. So the main argument for the holistic outlook is that education and sustainability in our contemporary times can only arise from a worldview that encompasses all our personal and social lives. So holistic education maintains that sustainability of society and humanity, and that means sustainability for all these 17 goals that we have for sustainable development. It can only truly take place when human beings have a worldview that offers society a holistic outlook, meaning every society in the international world today must have a worldview that offers a holistic outlook, so that we can look at the Earth, the whole of the planet as a whole. In fact, the 17 goals that we see here for sustainable development is really looking at everything as a whole. So therefore, holistic education. Now, before I go on, there are three development theorists known as Turnstone, Gardner, and Sternberg. When they spoke about intelligence, they spoke of it as a tree with many different branches, each representing specific form of intelligence. Although they formulated different distinct theories of what intelligence is, they agreed that it should be defined as a higher level capability, such as the ability to learn, comprehend, convey emotional knowledge, ingenuity, and imagination, and even an ability of adaptability in order to meet the challenges of the social environment. So when we look at traditional terms, Islam, then we have, for example, by the way, there's a book called Islam and Sustainable Development, looking at new worldviews, by Odeh Rashid Al-Juyusi, which is worth reading. It's been published by Routledge. Now, when we look at Islamic educational terms, we have terms such as tarbiyah, ta'lim, tadib, and marifa. Although education across the Muslim world is varied, not only in the modern times, but also in traditional times, these are the four terms that were used across the board. So tarbiyah refers to the social character development of an individual. Ta'lim refers to the acquisition of revealed and accrued knowledge. Tadib to good and polite manners. And marifa for wisdom, spiritual knowledge, and so on. Now, looking at the contemporary world, we notice that in recent years, in the West and in the wider world, an alternative education pedagogy to the current mainstream Cartesian Newtonian worldview has arisen in the form of holistic education, the one that I was speaking about. The main protest of this very wide and eclectic movement is that contemporary mainstream education has solely become about academic knowledge, materialism, and the obsessive focus on standards and testing. And so we have to remember that although this holistic education is grounded, has its background in the thinking of the West since the 1760s, it has its background in numerous indigenous cultures. And it is from this direction that the term, that we have a number of terms presented. These are words related to intelligence. So cognitive intelligence is already something that is mostly focused upon in mainstream education. But there are other terms that now have been put forth by holistic education theorists, which is speaking about emotional intelligence, spiritual intelligence, social intelligence, and so on. A holistic education, therefore, needs to be both integrated and interdisciplinary in order to achieve resilient sustainability. That the argument that arises from should go back one step further. So the problem with mainstream education is that it is incessantly qualified by cognitive intelligence alone. Although there have been several other approaches explained and even very much formulated by theorists, that has not been the approach of contemporary education. And one could say that that has led to a lack of morality, spirituality within the human societies in contemporary society where modernity has taken over or post-modernity has taken over. The argument from contemporary holistic education is that academic or cognitive intelligence has for more than 2 centuries been the main focus of our contemporary education. And of course, it has had certain amount of benefits. But it also has been unduly the only focus. So although there are benefits, we are looking at continuous widening lack of moral values and what could be possibly termed non-materialistic approach is also being removed from everyday education. It is evident that the majority of present-day practices related to sustainability are awash with cognitive learning, and in some cases, physical learning, meaning we are learning, for example, to deal with our physiques, how to be healthy physically in the sense of training our bodies. We may even have aesthetic intelligence in the sense of learning how to value art and music. And with all that, we are also learning critical analysis that may help us, assist us to intellectually understand and solve contemporary problems. Yet, what seems to be missing is the building blocks in education that promotes not only cognitive intelligence, but also, and to some extent, as I said, physical intelligence and aesthetic intelligence, but we also require emotional intelligence, spiritual intelligence, and even social intelligence. For example, being able to read the room, being able to read the current atmosphere, current situation, that requires not simply cognitive intelligence, it also requires emotional and social intelligence. So one educationalist, Raj, argues that such holistic education theory adopt the integration of ideals arising from numerous types of spirituality and humanism, which of course is rejected by mainstream contemporary education. So amongst the proponents of holistic education, there is an unanimous agreement that its main purpose is to nurture the inherent possibilities of human advancement. So there is no doubt that we need to redefine intelligence. Instead of simply the procurement of knowledge and acquisition of skills at the work market and overall improvement of, there is a need for an overall improvement of the physical, intellectual, social, emotional, and spiritual aspects of the individual. And that's where we have these terms turning up, which is cognitive intelligence, which is what our current education is based upon. It's about acquiring knowledge, information, understanding. Now, in the West, the development of essay writing in humanities, social sciences, making surveys, interviews, these are all developed within the world of cognitive intelligence, critical analysis, critical thinking, and that has been the focus of not only the West, but recently even in the East, where they're trying to develop these skills. And there is no doubt that there is a lot of benefit in this. However, we also seem to then miss out in education, emotional intelligence, social intelligence, and spiritual intelligence. So emotional intelligence is explained as the ability to perceive emotions, use emotions, to facilitate thought, understand emotions, and manage emotions, even to the point of promoting emotional intellectual growth. In other words, EI, which is emotional intelligence, is how we may use our emotion appropriately to control them under certain situations and manage our behavior and our interactions with others in the social environment. These abilities are now being studied and tested consistently through the social sciences of psychology, sociology, and education studies by using a number of skills and models. Study of social intelligence, not covered in mainstream education either, commenced with a scholar called Thorndike in the early 20th century. Now, he dealt with intelligent interaction with others. That was his field. So later academics such as Gardner would define social intelligence as the ability to perceive and respond successfully to others' moods, wishes, and their dormant or inert state of mind and capabilities. Meaning, social intelligence is linked to ourselves or our control in society, meaning controlling ourselves in society, our social expressions, our social sensitivity. Another scholar, Goldman, went on to describe social intelligence as the intelligence we use to proceed in our interpersonal world. In fact, he described social intelligence as it is like good social relations. And because good relations are like having good vitamins, and bad social relations are like having poisons. So, and he's the one who described the lack of social intelligence as the dark side. And it is defined by narcissism and Machiavellianism. Apologies for my pronunciation. So at the end of the day, that is social intelligence, which leads us finally to spiritual intelligence. If cognitive intelligence is about learning facts and thinking, social intelligence is about interacting, emotional intelligence is about feeling, then spiritual intelligence is about being in tune with the transcendent, and therefore it assumes the belief in something more than the physical or the material world. Spiritual intelligence, even by non-Muslim scholars, have been defined as being able to know something in multiple ways and being able to integrate the spirit with the outer life in the world. And there are numerous definitions of this. Okay, which leads us to how does this relate to the Islamic principles of education? My argument is that traditional Islamic education is very much a holistic way of looking at that. In some ways, there is a strong comparison between holistic education and education in the education that has been transmitted from the Muslim traditions. So how do we understand such terms, intelligence terms, in Islamic cultural context? Well, just as I mentioned those Arabic educational principles noted earlier, the terms tarbiyah, ta'lim, ta'dib, and marifa, there seems to be some links between the two that we can at least explore. So one of the things we can look at is these terms and how they relate to holistic education, holistic teachings. So ta'lim, which is the number 2, is very similar to the rubric of, or lies under the rubric of cognitive intelligence. And that is because transmission of knowledge, acquiring knowledge, thinking about rationally solving problems, all falls under ta'lim. Most Muslim scholars have always promoted holistic teaching. That is the argument. Although transmission and advancement of knowledge, which is known as ta'lim, was very highly regarded in Islamic tradition as well, it was never separated from altruism, virtuous life, spirituality, and the development of achieving wisdom. Islam promotes the building of an advancement of society based upon social values accrued from Islamic texts and Muslim experience. One can argue that without stressing all of these elements of education, there is a possibility of the Muslims omitting the emphasis that Islam puts on social brotherhood, social society, social living, empathy, kindness, public welfare, and therefore not being able to counter destructive emotional and social feelings. For example, feelings and social issues such as classism, racism, bullying at schools, fanaticism, all lies under not ta'lim, not cognitive thinking as only, but under social emotional intelligence. And when we're speaking about society, perhaps tarbiyah is the best suited terminology for linked to social intelligence. The reason is that the term tarbiyah refers to a wholesome education in general, but specifically it refers to upbringing within a social structure, meaning tarbiyah is about being brought up in a family, being brought up in a society, and so on. So the family is regarded as the smallest social unit where the upbringing and education of the human being first takes place. The education is characterized by social roles of the child, of the father, of the mother, and so on. Social care, social collaboration, upbringing, and protection. According to the classical scholar Fakhruddin Razi, the root words al-rab of tarbiyah have numerous meanings, where one meaning is al-tanwiyah, meaning growth and development. Furthermore, the al-Jawhari, for example, a lexicographer, spoke of tarbiyah, rabban, and rabba as meaning sustenance, nourishment, nurture, all types of socialization. There is no doubt that tarbiyah also incorporates much knowledge, manners, spirituality, but the focus of tarbiyah has always been socialization. And the socialization should be understood as through the concepts of justice, social justice, adl, and communal participation, that is known as shura, meaning speaking to each other as a community and deciding on the best solution. And that could be a small society, family, or it can be larger groups of people. This can be compared with contemporary theorist Goleman, social scientist, whose thoughts on social intelligence are that he argues that human beings, according to the latest findings in biology and brain science, are wired to connect socially. They have built-in predisposition towards empathy, collaboration, and altruism. But there is a condition for such a predisposition, and that is that the human being at an early age must be nurtured through the capacity of empathy, mutual aid, and kindness. And this is very similar to what Naqib al-Attas maintains, that human beings are encouraged to lower their wings of humility based upon the love their parents showed, which is very much an interpretation of the Quran. With regards to ta'deeb, that is, it denotes a moral and ethical commitment based upon Islam. Ta'deeb is about, of course, attaining ethics and manners. Ta'deeb comes from the basic meaning of disciplining yourself to be polite with good behaviors and manners. As the Prophet Muhammad himself said, I was sent to perfect character. According to the scholar, I'll just jump now because I think I may not have as much time. So the allegory may be provided by Al-Farabi in his book Fusul, classically, is perhaps striking for this type of education, which is the type of education to achieve morality. He offers an allegory of two individuals, where the first person learns all the sciences cognitively, but his actions are not morally good. Why acquire any of the sciences, yet his actions are morally good? Al-Farabi concludes that whereas it would be very difficult to change the first person's morality, it is the second person that is suited to become a philosopher. Because Al-Farabi himself was a philosopher. The idea here is that it is not just a cognitive intelligence can in fact be a problem afterwards to develop your morality. Whereas if you have morality, you can always learn the sciences. What is important to recognize here is that this understanding cannot be simply cognitive, but must be emotional, meaning having morality or having ethics cannot simply be cognitively. You simply understand it, you simply comprehend it. It has to be emotionally linked to an individual. So relationships of the individual, to be truly applicable, must be known through the heart and emotionally connected. Such relationship, may they be to the environment, may they be to the society, or may they be to the divine. All of them would be mere rituals if there is no trace of true feelings. So sincerity in worship, in ibadah, sincerity in social and legal relationships, sincerity as in the sense of behavior of morality and ethics, could only be achieved if we have emotional intelligence. In other words, emotional intelligence refers to a paradigm of emotional comprehension that involves the ability to read and access emotions of oneself and others. And therefore utilize such emotional information in everyday life to be effective virtuously. I have a quote here written by David A. Pizarro and Peter Salovey. They wrote, "The ability to be effective in dealing with emotions, accurately perceiving them, using them to guide thinking, being knowledgeable about complex emotional states, and being effective regulators of emotions comprises skills that come into play in being a moral individual." It's an interesting thing that these are also proponents of holistic education. And so Ta'deeb is not simply about cognitively learning about morality and ethics through reading the Quran or Hadith. It must be felt. It must be emotionally felt. And therefore, we have a requirement of achieving emotional intelligence. Finally, we have spiritual intelligence, which is paramount in Islam. In contemporary Western society, with regards to holistic education and their promotion of spiritual intelligence, that is related to a very wide range. And as we know, in Islamic world, that is more constrained in the sense of within Islam, spirituality is understood as part of religion. Whereas in the West, spirituality does not have to be part of religion. The definition of spirituality in the West has, in postmodern era, is devoid of any identification with religion. That is not true in Islam. Spiritual knowledge in Islam is commonly known through the terminology of marifa and through the action of tazkiyah, which means purification. It is to recognize that there is something wider, something larger in life than the material world and the people themselves. Okay, this type of spirituality is normally found under the rubric of Sufism. Hope I still have some time. It's around 11:30.
Hello, Doctor.
Yes. Yes.
Yeah, I'm sorry, but I'd like to inform you that you have 5 minutes left for
5
the
minutes.
presentation. Is that okay?
Yes, that should be okay.
All right, all right.
Okay, I'll just try to finish it in 5 minutes now. So, absence in educational pedagogy. All of these intelligences, beside cognitive intelligence, yes, was accidentally muted. So all of these intelligences that I've spoken about, except for cognitive intelligence, are unfortunately absent from our pedagogy and curriculum in both schools and universities. So the question that now develops is, how do we bring or implement such pedagogies and curriculums where we can develop these and where we can implement these intelligences in schools? And it is important to recognize that these are only the 4 basic steps of Islamic education and the holistic education. And there could be further elaboration from these 4 aspects. So this is just a very initial understanding of holistic education / education within Islamic culture. So one last step is interconnectedness. Holistic education is, its focus is on the interconnectedness, that as a human as a whole needs to be educated and therefore understand that everything in Earth, in the universe, is connected in one way or another. And in this way, holistic education is in perfect alignment with education in traditional Islam, because it should be interconnected and at the same time dynamic. This is something that our contemporary schools and universities should develop and research on. So it is important that not only foundational Islamic sciences which are pivotal, but other social sciences and humanities can offer us wider understanding. Sciences such as anthropology, sociology, psychology, political science, they all could be used in developing this mentality, this mindset, this understanding of holistic education. And in the Muslim world today, there's a desperate need to create a blueprint course design to explain how the various subjects within the world of education can be interdisciplinary and reciprocal relationship, how they can work with each other. And that specifically relates to Islamic sciences and social sciences as well. Now, I'm not going to speak about data collection, but there is no doubt that the education in the Muslim world, where it is now developing in Turkey and Malaysia, there is a need for a lot of data to be collected. What is going on the ground, on the grassroots of education, in the primary schools, in the secondary schools? Do we have bullying? Do we have narcissism? Do we have so many other issues? These arise due to the lack of holistic education. How do we then, how do we take these challenges? How do we create a quality education? First of all, collect the data. Different Muslim nations, different because of different social and cultural variables. And at the end of the day, implementation can take place after that for real sustainability, a real change in mindset. So to end, sustainability is a part of our worldview. It cannot be done simply straightforward without changing the mindset. During the coronavirus pandemic, in fact, during this period, societies have demonstrated too much their signs of narcissism, selfishness, materialism, and it demonstrates that excessive focus on cognitive intelligence in education that literally started during the Victorian time, exclusive of social, emotional, and spiritual intelligence, has been very destructive to the ethical and moral value of society. Instead of speaking about measure growth only by GDP and not values, we need to ask ourselves why we feel the world is our commodity and not a trust to be returned. Why we cannot acknowledge that a certain type of epidemic of narcissism is swallowing humanity today. Without changing that, we simply cannot change all these other elements in sustainability development, meaning all the goals that we have for changing and for developing for sustainability needs to take place from education onwards, because we need to educate people, and it simply cannot be done by simple cognitive intelligence, simply telling somebody, simply asking them to believe in it or understand it. It has to be done with various avenues. And as I said, we have social, emotional, and spiritual intelligence that needs to be touched upon. And maybe the argument is that we no longer feel, relate, or spiritually link with anyone beside ourselves or the extension of ourselves. What I mean by the extension of ourselves is us or our descendants, meaning humans and human descendants. That's what we're doing it all for. But here's the problem. Holistically, that's not really true. We are interconnected. Human beings are not separate from the rest of the universe. We are part of it. We are not separate from Earth. We are part of it. And therefore, this argument should be that we need to be sustainable, not for our survival alone, not for Earth's survival alone. It's a holistic survival. Okay, and some prophetic hadith comes to mind that I put here, that even if we were to be going, because let's say if the day of resurrection is about to be established and one of you were holding a palm shoot, let him take advantage of even 1 second before the hour is established and plant it. Planting a tree has nothing to do with survival. It has simply to do with the right thing to do, which is if you're planting a tree, do so. It's a part of the environment, meaning animals have rights, forests have rights, meaning trees have rights. This is not something new. This has been in traditional teachings for a long time. The earth is not our commodity. It is a trust that we need to return. In order to transform our mindset, Lars Watchman, another holistic education theorist and a climate supporter of environmentalism, argues it's not a climate crisis, but a societal crisis, and it has devastating consequences for the climate and nature. Thank you very much for listening. Apologies if it became a little too long.
All right, thank you very much, Dr. Amjad. It's a wonderful sharing session, because just look at the differences between mainstream education versus holistic education. We put emphasis on IQ, but not EQ. All right, let me just pick one question from the audience. We have a question from Puan Rosliza Ahmad. Yeah, nice sharing, Prof. She said. Just one question. How do you relate holistic education, or considering all the emotional and spiritual intelligence, with a deep learning approach? Can you briefly explain on this?
Can you just repeat that suddenly? Sorry, the sound.
Okay. All right. How do you relate holistic education with deep learning approach? Maybe that's a term in education.
I think they are connected, in the sense that deep learning approach is to learn things deeper, to go in depth into them. But I would say holistic education is taking different avenues. It's recognizing the need for not only going through the cognitive intelligence. You can, through cognitive intelligence, you can go deeper and critically analyze, deeply think about matters. You can even, what is known as contemplate on issues, meditate on issues. But they are not necessarily touching upon the different types of intelligences that are needed. For example, morality is something that you need to make a habit, not meaning morality does not happen. A person is not virtuous because at one point or another he thinks, okay, I'm going to help somebody. It's because he habitually helps.
Yes.
Deep learning. Okay.
Okay. All right. I hope that answers the question to Lisa. So we learned a lot about holistic education. Dr. Amjad actually explained about all the different intelligence, and that's a very insightful one. Thank you very much, Dr. Amjad. Okay, all right, thank you very much. Now let me welcome our third panel for today, the last one, Dr. Amir Shaharuddin.
All right, okay.
All right. So let me just briefly explain that you will have about 30 minutes, including the Q&A session for your part.
With this, we do have this Waqaf institution, and my institution is from Yayasan Waqaf Malaysia at the federal level. So I just want to share a few examples of the development of Waqaf land in Malaysia. For example, in Penang, from the government, federal government funding, we established, or we built affordable apartment in Penang, where this we built 77 units of apartments in Penang. It is cost about 23 million, and the project completed in 2018. And another example is affordable housing project also in Penang, where we built 152 units of condominium. This cost about 53 million ringgit, and it completed recently in 2020. And this is where the land is Waqaf land. The government come and give funding So the state and also the federal government work together to build this condominium. And also we do have this small project, but it's give a very high impact to our local society, where still example from Penang, they receive about 1.34 million ringgit to build 6 what we call premise, commercial premise of small commercial lot in where we built in Waqaf land in mosque. So this will give a return from rental of this shop lot will give a return to the mosque to generate income and also to sustain the economic of I just give my overview on this. So we do have a lot of Waqaf projects. For example, the one that I show in Penang, and also in Waqaf Malaysia, we do have we manage hotels. So we collaborate with Majlis Agama Islam Melaka, the state religious authority or council in Malaysia. Where they provide the land, Waqaf land, so the federal government come and build a Waqaf on the land. So we operate the hotel that we built on Waqaf land. So that is example. So so far there are 3 hotels that we manage. One in Malacca, one in Taiping, and also one in Kuala Terengganu in different state in Malaysia. That is another example. And the last one examples that I want to show is that Waqaf project, Waqaf initiative, where I think in Malaysia we are quite known with the Waqaf in Sultan Perak, Jalan Sultan Perak, where Waqaf that we built what Bank Islam, another Bank Islam on Waqaf land in Jalan Sultan Perak in Kuala Lumpur. So that one is initiative project taken by Tabung Haji. The funding come from Tabung Haji, and then another wilayah Persatuan provide the land, and we build Waqaf building in that land. So basically, when we talk about Waqaf, there are 4 main focus. We concentrate on this education, health, economics, and environment. So for this charitable project, there are 2 kind of projects. One is on this charitable projects, and also one is on the project that generate income to this Waqaf institution. So for example, the cash Waqaf that is collected by Waqaf Malaysia, we also mobilize them into sustainable project. For example, we purchase a building and we rent out the shop lot, the commercial lot, and this give income and generate income to Waqaf institution. And also we do investment of cash Waqaf, and dividend or proceed from the income will be distributed to the beneficiaries. So this is example. And another issue that I want to highlight is that there are a few challenges in managing Waqaf asset in Malaysia. First is we need more competent and skillful leaders and managers. And the second challenges is lack of funding available. We do a lot of, we have a lot of asset and Waqaf land, but only 12% is developed currently. And one of the main reasons is because of the lack of funding available. And the third challenges in managing a Waqaf, sustainable Waqaf project is that a lack of knowledge and awareness among public, because public also still maintain see that Waqaf is only for the religious purposes. For example, to build mosques, to build cemetery, or to build madrasah. But actually, Waqaf is bigger than that. The benefit can give a bigger impact to our society. For example, Waqaf for to generate or to stimulate economic recovery during the post-pandemic. So with that, because of that, in Malaysia, looking at the sustainable issues, we are in the process of finalizing our national Waqaf master plan, where we will concentrate on enhancing, first is enhancing capabilities on competencies of Waqaf institution. And second is to strengthen the current law and regulation that regulate Waqaf administrator and Waqaf project in Malaysia. Third is to diversify sources of Waqaf funding for Waqaf development projects. And the fourth one is to improve the level of awareness among our public. Moderator, I think I end my presentation here. Thank you very much for listening to my presentation.
Thank you, Master of Ceremony. Esteemed scholars, distinguished guests, ladies and gentlemen, salam sejahtera, salam padu, and salam kasih sayang. I am very delighted to welcome you in our national language and bring you the warmest greetings of Center for Foundation and General Studies, University Selangor. I am very honored to have all of you here in our international conference on Sustainable Practices, Development and Urbanization 2021, or fondly known as i-ConSPADU. This initiative is a continuation effort to our very first conference, the National Conference of Foundation and General Studies back in 2019. The pandemic had taught us, the academics and educators, the importance of adaptation and transformation in teaching and learning to ensure the continuity of primary, secondary, and tertiary education. We must swiftly design necessary reactions to make certain of the sustainability of quality education. The International Conference is one of our efforts in committing to the SDG goals to envision the 2030 Agenda for Sustainable Development. As UNISELians, the pandemic must not dampen our spirit and commitment to produce competent, upright, and ethical professionals and scholars. As Jacinda Ardern, the Prime Minister of New Zealand, mentioned in the general debate of the 76th session of the General Assembly of the United Nations last September, and I quote, "As we face interlinked global crises that demand actions, now is the time for us to recommit to the SDGs. COVID-19 cannot be an excuse for not achieving the SDGs. In fact, it is the further reason we must." I am very proud that our passion and commitment is shared by many people around the world. This could be seen by the number of papers and collaborators that participated in i-ConSPADU. With over 100 academic papers and over 10 collaborators from all around the world, I am very delighted to know that our commitment and aspiration in providing knowledge and sustainable quality education resonates with many individuals and organizations locally and internationally. Here in UNISEL, and certainly at Center for Foundation and General Studies, we prioritize the awareness of SDG to all members of PADU, fellow academicians and students. This could be seen in our integrated efforts of PADU members and government agencies in our past and current collaborations. One of our recent collaborations is the development of one of our general study courses, Human Rights in Malaysia, that witnessed the collaboration of PADU with the Human Rights Commissions of Malaysia. Members of PADU are also committed in keeping our environment green and sustainable. Apart from contributing to the green metric data, offering general courses such as green awareness and sustainability in community will enable us to impart the importance of good health and well-being, clean water and sanitization, climate action, life on land and below water, and also the importance of affordable clean energy. As mentioned by the Vice Chancellor earlier this morning, UNISEL is ranked 486 out of 912 universities around the world in our first debut at the UI Green Metric World University Ranking. Ladies and gentlemen, Aristotle mentioned that educating the mind without educating the heart is no education at all. We at PADU are aware of this fact. Therefore, whatever we do, we must ensure that our education practice must not just enlighten the minds, but also the hearts, the soul, and the human body. This is the very reason PADU is established in UNISEL. We are here not just to provide the foundation courses in various fields of studies, but we are also here to train our students' hearts, soul, and physical well-being through our general courses that we offer here to the UNISEL students. At times, we need more ideas from new partners who are experts in their field from all walks of life. Therefore, I invite all of you to help us fulfill our call and mission to the community through collaborations in research, publications, international conferences, and industrial links. Before I end my speech, I would like to thank all collaborators, the organizing committee of i-ConSPADU, and all of you, ladies and gentlemen, for your efforts, dedication, and enthusiasm, and your pristine knowledge and insights through your commendable efforts in your research. Until then, thank you and have a pleasant day.
Dr. Maegala for the inspiring speech. Ladies and gentlemen, the time has come for the announcements of winners. Best Speaker Award, Business and Management category. Best Speaker goes to Dr. Kamisa Supian. Silver, Associate Professor Dr. Nur Azila Hussain. And finally, bronze, Madam Nur Hasbi binti Abdul Samad. Moving forward to the next category, Best Speaker Award for IT and Communication. Gold winner goes to Ms. Marmara Gharib Al-Jadi. Silver goes to T.S. Muhammad Fairuz bin Abdul Rauf. And finally, bronze goes to Professor Madya Dr. Haslinda Sultan Ahmad Nawi. Moving forward to Best Speaker Award, Science and Technology. Winner of gold goes to Mr. Muhammad Shahir bin Muhammad Isgan. Silver goes to T.S. Nur Halini Baharin. And bronze goes to Mr. Ahmad Naufal Bintun Tamanian. Moving forward to best paper for category of social sciences and education. The winner of gold goes to Ms. Nur Shahira Binti Azman. Silver goes to Madam Sophia Chia Binti Azlan. And finally, bronze goes to Mr. Muhammad Anwar. Congratulations to all the winners. Ladies and gentlemen, with this marks the end of today's event. On behalf of the organizing committee, we would like to extend our appreciations to the guest of honors, the keynote speaker, the panelists, collaborators, and the participants who had joined us today. We are greatly honored by the immense support to the program. Congratulations once again to the winners. With this, ladies and gentlemen, I wish you a great evening and Assalamu alaikum warahmatullahi wabarakatuh. Thank you very much.